is SeKang Kwon, and this project is joint work with 고성진, 세우상, 임혁호, 정은기, Professor Hyuk-jung Kwon, and Dr. Adel Sobi. Professor Kwon and Dr. Sobi are our advisors for this work. I'm very honored to be invited here. We are going to talk about leadership problem over time function. We studied its quantum solutions and implemented it in a real quantum device. In this talk, we show the performance and limitations of quantum computers in the disk era. Let's start with our motivation. We are motivated from finding quantum advantages, and the leadership problem for band functions is one of the problems that we can find quantum advantages. The reason is that when it comes to band functions, the leadership problem can be reduced to abelian cases of subgroup problem, so it can find quantum advantages. One of the applications of leadership problem is related to Poly 105. Poly 105 is a massive authentication code. It is widely used when sending messages. Bonnet-Tan and Naya paper, they built quantum attack on Poly 105 based on leadership problem. And let me introduce the leadership problem. Let f and g are band functions defined on d2 to dn. And a band function is a special type of linear function. When even f and g satisfy this equation for all f in g, what you have to do is to retrieve the leadership. Also, we assume that there exist oracles that compute f and g. Let me ask that how many times do we query the oracle? The answers in this table. As you can see, the quantum algorithms are exponentially faster than classical. There are two quantum solutions we introduced. The one is called Rattler's algorithm. In this case, f tilde is given. F tilde is the Ray-transform function of f. The other is called Rattler-Gavinsky algorithm. In this case, f tilde is not accessible. So the latter case is more general. In the Rattler's algorithm, the key idea is that for Boolean functions, the quantum Ray transform is equivalent to the Hadamard transform. So we can calculate the Ray transform easily by applying Hadamard gates only, like this. Here is our result. In this example, we said the leadership S is 1 over 1. The simulation results, we can get the solution with 100% probability. On the other hand, in a real device, we can get the solution with about 60% probability. Anyway, this noise level, it seems that this noise level is negligible. And This is Rattler-Levinsky algorithm. As I mentioned before, in this case, we cannot access to the Fourier transform function f. Here is the circuit. After the measurement, we get b comma y string, and this is not the English set. The previous algorithm, we get S state after measurement. Instead, in this case, the bit string b comma y is orthogonal to 1 comma s. However, this means that b comma y string is orthogonal to 1 comma s, and I think the word orthogonal, not in the usual sense. We define the orthogonality by this dot product, and this dot product is defined by this modular 2 addition. In this example, to retrieve it, we choose 4 different states from this outcome, and scatter them into a system of linear equations like this. And by solving these equations, finally we get x like this. In this table, we can check that s comma 1, the dot product of s comma 1 and y comma b is always equal to 0. These are calculation results. Here are our implementation results. In the real device, there are too many states compared to simulation results. We expected only 16 states like simulation results, but there are too many. So we have to distill out some wrong states. But it is hard to do because the probabilities are not dramatically different from each other. So we conclude that in a real device, this algorithm does not perform well, we think. And although this algorithm is fragile to noise, we guess that much of the errors came from topology gates. Topology gates are made of the oracles. In the oracle, there are 2 topology gates and 1 SeKang gate, and we need more swap gates to implement it. And as you know, they are likely to cause noises. Then we summarize our results. We implemented 2 algorithms, and we show that Rattler's algorithm performs well. However, the Rattler-Levinsky algorithm does not provide the meaningful results because of noise. And the error originates from the topology gate we get, which need heavy resources. So we recommend as future work, it is good to do noise analysis on topology gate will be good. And this is our GitHub repo. If you are interested in, please check this out. Thank you.